Hello, this is Matthew Harms from EMA. In this demonstration, I'm going to show you how to do an impedance check and coupling coefficient check for a selection of nets that you have in a board file. In my example, I'm going to be using OrCAD PCB Editor as my board tool of choice with a file in that format, although you could use board files in nearly any format you want. In this example, I have a couple components that I'm interested in taking a look at. So the ones that I want to see are the nets that are between component U1, that's our FPGA, and the connector here J1 and J2. So those are the nets between those components are the ones that I'm interested in for this DDR analysis. So I want to find out the trace impedance of those nets at various places along their length, as well as the coupling coefficients, so to see how closely they're coupled. One thing I want to point out before I move this across to the signal integrity environment is that for my nets, my DC nets, I've given them a property of voltage equal to the value that they're equal to. That just makes my analysis in Sigrity a little bit easier to get going, so I don't need to do quite as much setup. So that's been done in advance. What I need to do to bring this over to the Sigrity environment is open up this Sigrity Suite Manager, and in there I'm going to open the Speed Links tool. This is going to allow me to translate my board from the BRD format that I have there into the SPD, so the speed format that Sigrity wants. We can translate files from most any board format out there and bring it into the Sigrity environment. So in my case, I'm going to be using Speed Links to bring in the OrCAD PCB Editor board. So we can open this up with whatever license we pick. Right here, I'll just use that one. I'm going to browse for the file that I was just taking a look at, which is this board file right here. And I'm going to translate that into an SPD format. And hit translate. And that's just going to take a few seconds and translate this board over to speed format for me. Once that's complete, I can just exit out of here. It actually exits for me. And now to do my analysis, I can invoke any of the tools down here. The tools that contain the licensing that I need is either Speed 2000 or PowerSI. Either of those two tools will allow me to perform this type of analysis. So we can use the Speed 2000 simulator or the PowerSI tool. I'm going to choose the PowerSI tool. In this case, I'm going to choose a license that I want to use. And once the tool is invoked here, I'm going to load the layout file that I just created using the SpeedLinks tool. And here comes that file. So we can poke around here and take a look at the different layers that we have in this. So this will correspond exactly to the file that I just had in OrCAD. But now I'm taking a look at it in the Sigrity environment. The workflow over here helps us go through the steps that we want to. We want to make sure we're on the right flow. I'm on the trace impedance coupling check flow, and that's the flow that I want to run through. So I loaded my layout file. Next you can check your stack up. And this is bigger than you're able to see in your window, but here's the stack up that it brought across from my board tool. I'm going to hit OK, that's fine. Next I can prepare the nets. And in my case it's going to be pretty easy because of that voltage property I told you about. There's really no setup that I'm going to need to do here. I can take a look at my nets over here on the right hand side, and I can see that my power nets are already defined as power nets because of that voltage property, and my ground nets are also defined. I have a bunch of other signal nets down here that I'm going to kind of prune down a little bit using the setup net groups. So first I'm going to switch to enable trace check mode, which is just the analysis mode that I want to be in to run this analysis. And then I'm going to set up my net groups. To set up my net groups, I want to go from component U1. I want to find the nets that go between component U1 and component J1 and J2. So I'm going to search for a component U1. It's right here. That's my transmitting component, and my receiving components are J1, J2. Those are my DDR connectors there. So I'm going to hit next. It finds these power nets that are connected between those two components. That's fine. I'll hit next. And then it's going to show me all the other nets that are assigned between these two devices. I want to first take a look at all the single-ended nets. And so these are all the single-ended non-differential nets. I want to include only the nets that go to both components, not these ones that only go to J1. So I'm going to uncheck those right there to get rid of them. And now I have all the single-ended nets that go between J1 and J2. I can give these an interface name if I want to, so I'm just going to select all of these and I'm going to call them single, just to make it a bit more clear the type of net that I'm analyzing, single-ended nets. And with that, I can hit finish. So this is just a summary of my net group, and with that I'll hit finish, and I can take a look at my net group now down here. So here's my net group, and here's all the components that are in there, or all the nets that are in there and the components that they're touching. So that looks good so far. What I want to do next is I want to set up another group for my differential nets. So I'm going to set up another net group right here. I'm going to go again from U1 and take a look at that at my driving component to J1, J2. And there's my power nets again. And this time I want to see my differential nets and not my single. So I just want to see my differentials. First I'm going to turn these all on. I'm going to select them all to turn them all on first off, and then I'm going to turn these couple here off. I only want to see the nets that go between J1 and J2. So there they are, all my differential nets that go between J1 and J2. I'm going to give this a prefix as well, just so I can hopefully find this later on. I'll call this diff for now. And there it is, defined as diff now. And I'll hit next, and that makes me my net group with diff in the front. I'll hit finish. And if I collapse this, now I can see my differential nets here at the bottom and my single-ended nets up there in the first net group. So I have two net groups defined. I've split them up to between differential and single-ended. And once I've done that, I can set up my trace check parameters. So this is the type of analysis that I want to do. I want to do impedance and coupling coefficient. My coupling percentage is up to 2%. My rise time, 100 picoseconds. And I want to check by net group. So I have a net group set up. I just set up those two net groups. So that's how I would like to do my analysis by net group. I'll hit next here. And it's just showing me the net groups that I've set up. That looks great. I'll hit finish. And that should be it. I'm just going to hit save here, and then I'm going to start the simulation. So here's save, get it saved off. And then we're going to start the simulation here. So here goes start. And that's just going to take a second. You'll know that I didn't attach any models to anything. I didn't do that in the schematic, the PCB, or the Sigerty end. I haven't attached models anywhere. This is doing a geometrical based simulation and is going to give us results with very minimal setup, as you saw here. All right, now the simulation has completed. We can take a look at our net impedance summary, our net coupling summary. I want to go to take a look at the impedance plot and impedance plot expanded, both collapsed and expanded, and this will show you our net group results. So let's take a look at impedance plot collapsed first off, and I'm going to clean up some space here. And what we can see here is all the different nets that we have in our single-ended net group and what their impedance is as we go along. So you can click on nets, it'll highlight them for you. Or if you want to take a look at some outliers here, you can find out where does this higher trace impedance occur. So we can double click on that. It takes you immediately to the board where you can see exactly where that unusual trace impedance occurs in your board. And we'll take a further look at those in a second as well too. We can also see the impedance plot in the expanded format, so you can see the different traces with their different trace lengths based on the overall length in millimeters. So here's DDR3 DQ13, and it has a trace impedance of 64 for the first 15 millimeters, and then about 60 ohms for the remainder of the length. So you can see the length as it goes along. Here's some that have some impedances that change as it goes along, probably due to discontinuities in the return path. You can see a table of the results if you want to, just by clicking on table. It shows you every segment of every trace and what it all is, the percentage of the overall length, the impedance of that, the length in millimeters as well. And you can also see the impedance overlay in the layout results. So if you want to see this right in the board view, you can do that here as well. So here's the result in the board view. If you want to see the coupling coefficient plot, you can see that as well. So let's take a look at the coupling coefficient. This shows you your coupling coefficient plot collapse. So this shows you just all your coupling coefficients for the single-ended nets all together. And again, if you want to find one that's of interest to you, just select it, double click it, and it's going to highlight for you that coupling coefficient, and you can see why it's getting coupled, probably due to this event trace right here being so close to A10. You can view the expanded view. This shows you the traces expanded, and each trace now you get to see the coupling and how much coupling is being induced on it, and use this legend on the graph. You can see the table with very specific results for every trace, and you can see the overlay and layout as well too. So if you want to see exactly where these traces are getting some additional coupling from, you can see that overlay and see those traces and where that coupling is coming from. So some very useful results. Let's go back to see this one more time, and I'm just going to switch to the differential view. So here's coming up now the differential nets that we had taken a look at, and we can see their results now as well. So here's the results for the impedances for the differential nets. You can see there again pretty uniform around 60 ohms. You do have some outliers here again that you could click on and determine where they exactly are, so it brings you to the sections that are problematic for you. You can see the expanded view of the impedance just like before, the table, as well as the impedance overlay on your plot as well. So you can see all that information that we saw previously. Interestingly, here's the coupling coefficients. So you can see the coupling coefficients collapsed, and you can see the list of those here and expanded. You'll notice now that the coupling coefficients for the differential traces are much higher. I like to separate the differential from the singles so that the differential results don't get mixed up with the singles and make you think that traces that shouldn't be coupled are, because they're just coupled with each other. But here you can see the coupling between the nets, and in this case you almost want to make sure that the coupling is high for your differential nets. You can see the table here again, and you can see the overlay again in the layout just to see those results that way. I was taking a look at the results between U1 and J1. If you want to switch between U1 and J2, you can see that as well just by dropping this down to select J2, and you can even drop down the net group to show the single-endeds as well. And once that's displayed, you can see the single-ended nets going from U1 to J2. You can take a look at all the same information as you did before. So the impedance plot collapsed, expanded, the table, the overlay and layout, and the coupling coefficients as well too. So you can see all kinds of interesting stuff, and try and from there determine where problems are and what you need to fix. What you can do next is you can generate a trace check report. So instead of capturing screenshots for all of this and documenting everything that you've done, you can simply click to generate a trace check report, and that's going to go through and do all of that work for you. So I'm going to click that. It's going to go through and make all my reporting for me in an HTML file, which I can then send to anyone, then they can view in their web browser. I'm going to hit OK, and it's going to go through and generate that report for me. And once that's generated, here's your HTML report that you can view right in the Power SI tool or in any web browser that you choose. So it has all the information about things like your stack up, your trace impedance nets that you're checking, and the groups that you have set up right here. And beyond that, it has your coupling check summary results. So all the results of that simulation in tabular format, and then your coefficient summary table, again in tabular format, and then some graphical information. So it shows you your net group with your single nets and the results from that, your trace impedance collapsed, your expanded impedance report, and then it gives you some overlay results as well. And it just continues giving you all the information for all the net groups that you have and all the different layers that they're on, just layering you with information that you can then arm yourself with to make intelligent decisions about if this might be good enough. And if it's not, of course, you can then take this and do some further signal integrity analysis on these nets. So if you think there might be a problem that you need to do further research into, you can start assigning some models and taking a look and seeing if that problem is indeed a problem or if you need to make some changes to it. All right, thank you for watching. Hopefully you enjoyed this demonstration of the Sigrity tools, and the functionality of finding out your trace impedance and your coupling coefficients for your nets in a design with no model assignment needed and using any board file that you have. All right, take care.